The speed of light is constant. Well, it is one of the most iconic or commonly heard phrases in physics, and that marks the beginning of Einstein's special theory of relativity and our second lesson in our journey of understanding what is special relativity. Well, when we talk of the speed of light, today we take it for granted now, but this statement actually changed everything. The speed of light is constant. Now, when we talk of the speed of light, we should understand that it does not depend on how you measure it. That means whether you're standing still or you're flying in a rocket or you're orbiting around a black hole, the speed of light will always be constant. That means light will never go faster or slower. It is one number that universe or the nature does not negotiate with. So we cannot say that the speed of light is constant, not almost, or not depends on how you measure it. It is always the same, 300 million meters per second, as we will see that this figure actually changes and rounds it up. So it is one of the number which universe and nature neither negotiates, and when we cite this number, we are actually talking about the structure of reality itself. The speed of light is constant. But the question arises when we are talking that this is so fundamental, so very intrinsic in our learning of relativity or relativistic physics. The question comes is that why should we at all care about it? I would say, how does Albert Einstein comes into this picture when we are talking of the speed of light is constant? Now, in order to know that, we have to rewind our memories a little bit to the past, rewind to a time when physicists and mathematicians were struggling to understand the speed of light, and what we see is something great. So we are typically talking about an era or about a timeline around about 1600 to 1800, and this was the time when the physicists were trying to solve out and figure out what is the speed of light. And the first important person, a Danish astronomer, calculate what is called a finite speed of light, Ole Christensen Roemer. Now, remember that when Roemer was doing all his calculations and experiment, he was not trying to measure the speed of light. Rather, he was trying to observe the eclipse of Io, which is one of the innermost moon of Jupiter. And this experiment is profound, is so very interesting that it actually tells you a remarkable story. This story actually marks the beginning of measuring light at a finite speed, and this marks the entire path of Einstein's special theory of relativity. Now, right on this picture, as you can see, that this is a credit which has been from ESA, that this is the Io, this is the innermost moon of Jupiter, which is going on and on around, and it is roughly calculated around 42.5 hours. So when astronomers thought that they could predict when Earth was moving closer, as you can see in this animation, that when Earth was moving closer to Jupiter's orbit, it was thought that the eclipse of Io would appear earlier than predicted. And when Earth is moving a little bit further away from Jupiter, eclipses appeared later than expected. So considering this moving closer to Earth and moving away from Earth, what Roemer thought was that it should not be something instantaneous. So Roemer thought that maybe the light from Io takes time to reach us, and when Earth is farther, it takes longer, rather than when it is nearer or closer, it takes less time. So from here, inference can be drawn. What Roemer thought actually is that it means that light does not travel instantly. That means light has got a kind of a finite speed. If the orbit of Io creates an eclipse which is earlier when it is nearer and later when it is further away. So Roemer actually, what he did is that he didn't exactly knew how to calculate the distance from Earth to Jupiter, because the fact was that astronomy was not that precise during that time. So what Roemer did is that he found out the total delay of Io's eclipse, which was about 22 minutes or so, and he assumed that this delay was due to the light taking extra time in order to cross the diameter of Earth's orbit. So the speed of light which he calculated is something around this, and this is almost close to the limit that we think of today. So although it was not exactly right, but it was remarkably closer to the limit that we talk of today. So the importance is that Roemer was the first person to prove that light travels at a finite speed, He was the first to use astronomical observation to estimate a fundamental constant of nature, and what we would see that Roemer was the first to suggest that light has a finite speed, but just how fast it is. That question caught the attention of another person whose name was Christiaan Huygens, who does not just want to guess, but he wanted to calculate it. And this brings up to the next part of our video, a very important insight and a very important contribution of Christiaan Huygens. So during that time, when we are talking about Descartes and etc., were thinking that light would travel instantaneously, but he did not measure the speed directly, but he argued logically. So here you can see that what he actually thought is that he used refraction, that is the bending of light through glass or water, and to support this he realized if light moves instantly, then how can it slow down in denser media like glasses? So this was a kind of an indirect proof of a finite speed. So he imagined every point on a light wave front acting like a new tiny source of waves. So this animation actually shows you, and this is typically which is called the Huygens principle, that every point on a wave front can be treated as a source for secondary wavelets. That means that this new wavelength is the envelope of another wavelength, and so on and so forth. So this was Huygens' insight that if it is bending, I mean to say in case of a denser media like glasses etc., so that means it cannot be instantaneous. It has to be something finite. And this Huygens principle actually we will see later led to a lot of important insights and understanding. So remember that Huygens was the first to challenge that the idea of light is instantaneous using physical reasoning. He anticipated waves' behavior, for example diffraction, interference, long before it was accepted, and his theory explained why light bends when it enters a different material. Remember that although Newton's particle theory was very dominating during that time, Huygens' wave theory came back strong later when we use and when we will see Maxwell's equations. Well, Huygens gave us the first estimate, but nature had one more clue hidden in the night sky. A few decades later, we come across another English person, James Bradley, who was looking up the stars and noticed something different. Well, James Bradley was an English astronomer and priest who served as a third astronomer royal from 1742. Now, Bradley was trying to measure what is called a stellar parallax. Now, parallax is basically a kind of a tiny shift which happens in position of nearby star due to Earth's motion around the sun. And this would actually help to prove the Earth's orbit around the sun. But instead of studying parallax, he found something else. And what did he found? He found that the apparent position, or I would say the stars appear to shift position slightly, not because of parallax, because the shift depends upon the direction of the Earth moving in the orbit and the angle of the incoming starlight. So this phenomena is what is called a stellar aberration. Let me give you a very simple example of what Bradley was trying to find. Right on this on your screen, you can see this is a kind of an animation. You can see a celestial sphere full of stars, and you can see there is a red arrow moving, which is showing the Earth's orbital motion around the sun. So as the Earth moves, the apparent position of stars seems to shift. They trace small loops or ellipses all over time. So this strange apparent shift of the star's position, because light it takes time to reach the Earth, and the Earth is moving while that light is arriving. So in order to demonstrate that it is not caused by the stars moving, but actually by the moving light, I would like to give you a very simple analogy of what Bradley thought during that time. Imagine that you are walking in a rain. Imagine that you're walking in the rain, and if you're standing still, as in this figure, the rain falls straight down. But if you start walking, the rain appears to come a little bit at an angle. So you have to tilt your umbrella and in order to keep yourself dry. So Bradley realized that starlight behaves in this way. So because of the Earth is moving while the light is still arriving, so the telescope needs to be tilted slightly to catch the light. So this tilt actually proves that light takes time to reach us and it does not travel infinitely fast. Now from this we can find that Bradley has confirmed that light takes time using the star and Earth's motion, but watching stars was not enough anymore. A new generation of science, and he calculated the speed of light approximately this is 30100 kilometers per second. So watching the stars was not enough, and a new generation of scientists was willing to catch the light motion here right on Earth, and we come across Armand Hippolyte Louis Fizeau, who was a French physicist who in 1849 measured the speed of light within 5% accuracy. Now, what was this was a big deal. Before he actually designed an experiment to measure the speed of light, and Fizeau was the first to bring in the lab and succeeded using just mirrors. And we will see light beams and a kind of a toothed wheel. So this was an arrangement of Fizeau's experiment. So we have got a light source here, a beam of light emitted originally from sunlight. Then we have got a toothed wheel as the light passes through a rotating wheel with evenly spaced teeth. And then we have got a distant mirror. The light travels a mirror placed at around 8 kilometers away, and the mirror reflects it back to the wheel. So this was a kind of an arrangement what Fizeau was making. Apart from James Bradley's parallax, he was doing it right on his laboratory. And here you can see the key idea was as the wheel starts spinning, light passes through a gap between the teeth, and it travels to the mirror and comes back. And if the wheel spins slowly, the light returns through the same gap. But if the wheel is faster, a tooth moves into place before the light returns, blocking it around. So the speed of which the wheel was turning just disappears, giving the time to take a travel round the trip. And again, this was almost close to what we measure, around 792 kilometers per second. But this was the measurement of Fizeau right on the lab, and he found that light has a finite measurable speed, and it can be determined something on the lab with certain terrestrial instruments. Now, with Louis Fizeau coming up with defining things which are right on the laboratory, this was further taken up by another French physicist, Jean-Bernard Léon Focault, who was a French physicist best known for his demonstration of the Focault's pendulum, which actually demonstrates Earth's rotation. Well, this brings me to a very important out of the topic way. There's a book called Focault's Pendulum by Umberto Eco, and it is an amazing read of crime and mystery and thriller. Same Focault's pendulum. Okay, coming back of the topic, in 1850 he developed something which is called the speed of light in the lab, improving on Fizeau's method. And what did Focault find out is that the speed of light, just like Fizeau showed. So from here, when we take up to the next part of our video, what we find is that the speed of light is finite. Light travels slower in water than air, directly confirming that light slows down in denser media. A huge win for the wave theory, and he gave an even more precise estimate of light speed, and he found this one, 298,000 kilometers per second, which is almost equal to the accepted value of 299,792,458 meters per second. Well, that is how things actually happen. So with all those physicists coming up, Roemer, Huygens, Bradley, Fizeau and Focault, we first found out that light moves with a speed, with a precision, and this is always finite. Now with all these physicists coming up, as you can see, these are the era, and this is how it has been measured. So we find Roemer, he did it with astronomy, taking out that light takes time, not finite. Christiaan Huygens, he did it with the theory, wave theory and logic. Then we come to James Bradley. Again through astronomy, he proved finite speed again. Then it comes to Fizeau, who did it with terrestrial instrument. And Focault improved on Fizeau's experiment, and he found a more accurate and proved light slows in water. So from all this, what we can find finally is that the speed of the light, this is constant, and it is around 671 million miles per hour, and to be precise it would be 300 million meters per second, and to be more precise it would be 299,792,458 meters per second. Now, with taking up all this speed and this calculation with Roemer, Huygens, Bradley, Fizeau and Focault, the problem was still there, that we are not being able, the physicists were unable to understand what light actually is. I mean to say, they calculated the speed of light to be finite. They calculated using terrestrial instrument, astronomy, everything, but what actually light comprises of. And that brings us to the next part of our video, which we call it as electromagnetic wave. Now, while Fizeau and Focault were racing to measure light, two other minds were working in a deeper mystery. What is actually light? And Michael Faraday, without formal mathematics, discovered something very astonishing. He saw invisible lines of force swirling in space. And then came James Clerk Maxwell, the mathematician who actually gave Faraday's vision an equation. When Maxwell wrote down the laws of electricity and magnetism, something unexpected emerged. What was that? Let us look in the next part of our video. So Michael Faraday actually discovered electric and magnetic fields are linked with each other. So through his innovative experiments, he found that a changing field creates an electric field. So a changing magnetic field would create an electric field, and a change in electric field would also create a magnetic field, and vice versa. So this was a kind of a handshake. A mutual handshake hinted that electric and magnetic fields could sustain each other as waves even in vacuum, and there is no medium which is required. Then came James Clerk Maxwell, and he took Faraday's ideas and wrote 4 equations that governs all electricity and magnetism. I've just shown the differential form, they're an integral form. However, I've made a separate video detailed on Maxwell's equation, which you can look on my on my YouTube channel, Physics for Students, which you're watching right now. So what did these equations actually tell? One is tell that there's a disturbance in the electric field that creates magnetic field, which in turns create another electric field, and this disturbance can travel through space like a wave. So considering all the Maxwell's equations, what we get is a kind of a ripple. A kind of a ripple that travels through space. Right on the animation you can see E, which means the electric, and B is the magnetic field. So the electromagnetic disturbance always travel at a particular speed. And what Maxwell found is that that speed is 671 million miles per hour. Irrespective of the wavelength. Now you can see right on the top the wavelength is a little bit longer. Right at the below this fellow is coming, which is a little bit a shorter wavelength. Irrespective of whether it is short or long, I would say the electromagnetic wave travels at 671 billion miles per hour. So the question arises, how did Maxwell's equation led to the idea that light or the electromagnetic waves do travel at a finite speed? So we won't go in details of these 4 Maxwell's equations. What happens is that this animation which you can see, Maxwell actually showed that if you can change the electric field denoted by E and the magnetic field denoted by B, remember they are all perpendicular to each other, you get some kind of an equation which is this. Now don't worry what this equation is all about. We are taking a step-by-step approach. So this equation is typically called a wave equation. We'll come to what do I mean by wave equation. But let us break down this equation. If you take the left-hand side, it shows that how the electric field is accelerating or changing over time. It is a second-order differential, so it is twice. This part of the equation typically called a Laplacian. This is how the electric field is curving or spreading over space, and you all know that this is the speed of light denoted by c. So it is just like the way a ripple spread across a pond. The shape of the wave is controlled by how it curves space and how it changes with time. So going ahead with this, we found out that light is just a ripple, and the math, actually the equations, tell nothing more than how fast that ripples move. So considering from Maxwell's equation, we get something like this, and this is very simple. This epsilon naught is an electrical constant, this mu naught is also a magnetic constant, and c is something we are about to calculate, that is the speed of light. So if we just plug in the constant values, what we get is this, and from there we get this one, and approximately we get to 671 million miles per hour. So we did nothing, Maxwell, I would say. We just plugged in the values, and by substituting the values, we get this kind of an electromagnetic wave speed. So Maxwell actually, so this is approximately equal to this. So Maxwell actually took the constants from electricity and magnetism, and we get the speed of light. So we can say that changing electric field generates magnetic field, and changing magnetic field generates electric field. And we came to a conclusion that they are not two forces, they are manifestation of the same thing, which is now termed as the electromagnetic field. However, there is a question. Now, when we are talking of this particular equation, we are talking of electricity and magnetism, but all you can see are all these E's. That means there is only electric field. What is the magnetic field, which is denoted by B? Because it has to be both electricity and magnetism. Now, in order to know that, as I was telling, that let us consider this to be an electric field. What do I mean by that? An electric field is something that can push or pull charged particles like electrons. You can see the minus sign is attracting, the plus sign is repelling. And we also have a magnetic field. What does it do? A magnetic field can push moving charges or magnets, right? So normally we think these fields come from batteries or magnets, but in empty space, even without any of these things, the fields can still exist as waves. Now we come to what we are calling of a wave equation. Oh, what is a wave equation? Nothing else. It is just a kind of an equation that tells you how something moves like a wave. So like a ripples on a pond, or sound waves in air, fields can ripple too. So from here what we can understand, that if you take when there are no charges, right, when there are no currents, for example, vacuum conditions, ideal conditions, you can combine Maxwell's equations and you get two separate wave equations. For the electric field you get this, and it follows actually a wave rule, and for the magnetic field you get another equation and it follows the same rule that is for the magnetic field. And here is the beauty. If you combine both of them, it actually tells you this one. Both the electric and magnetic field obey their own wave equations, and in empty space they don't need wires or charges. They ripple forward supporting each other, and this equation actually tells you that. So when Maxwell combined these equations, he discovered that the electric field and the magnetic field, each one of it has got a kind of a behave like a wave. So wave equation travels at a speed with this, and we have seen that how we substitute the value and we get the speed of light. So what he showed is that both fields satisfy wave equation that describes waves traveling at a speed, and that speed turned out to be the speed of light. So from the Maxwell's equation, as you can see here, what we get is that speed is equal to the speed of light. So what was Maxwell actually trying to prove? Well, when we see this kind of electromagnetic ripple around our space, so he concluded that if the speed of electromagnetic disturbances or ripples is equal to the speed of light, then obviously light itself must be an electromagnetic disturbance. It must be an electromagnetic wave. So if the speed of the electromagnetic disturbance equals to the speed of light, so light itself must be an electromagnetic disturbance that permeates our space. So from this, that was a big step towards unification. We now have an understanding of what actually light is. It is nothing but a kind of a disturbance, an electromagnetic disturbance, which is called an electromagnetic wave. However, there still lies a problem. And the problem is this. Now remember in my earlier video when I talked about speed, the speed of light, right? When we talk about speed, we need two things, right, which should be synced to each other. When we talk of the speed of this car, we tell that the speed of this car is relative to the road. When we talk of the speed of the sound, we talk of the speed of the sound relative to the still air around. When we talk of the speed of water, we talk of the speed of water is relative to the still water. But what about the speed of light? What was the thing? What was that thing or object that is relative to the speed of light? Well, that is a question which led lot of confusion among the physicists, mathematicians, and the whole era actually went to understand this problem. If everything in this universe we are talking of speed is relative to something, like the car is relative to the road to this, and the sound is relative to the still air, water is relative to still water, what was the thing that is relative to the speed of light? Well, in order to answer that, we are going to take a pause, and this is what I am going to take up in the next part of my video on special theory of relativity. So thank you very much for watching. If you have liked my video, please do not forget to subscribe to my channel Physics for Students and click on the bell icon to get all the notification from Physics for Students. This is my other channel, General Relativity. You can follow me on my LinkedIn profile, and you can write to me for any other confusions or any things that you want to discuss about career, physics and mathematics. Please let me know in the comment box how this video series is going, and we will be back with more important videos on special relativity and subjects and important podcasts coming up in this month. So we will be there, and please do let me know about your comment. See you very soon, but till then, may the good Lord be with you.